Today I'll discuss the optical emission spectra from semiconductor lasers, and then lead on to try and see how gain is calculated in a semiconductor laser. Now, the optical emission spectra will depend upon the spontaneous recombination as well as stimulated recombination. Since we are interested in lasers, we are more interested in the stimulated emission process. And also during this discussion, we'll see that according to the Shockley-Van Roosbeek relation, emission and absorption are related. Okay, so we'll try and use the Shockley-Van Roosbeek relation to relate the absorption spectra and the emission spectra. You know, for a semiconductor, absorption spectra is very easy to determine. Okay, so a typical absorption spectra in a semiconductor will be, say, alpha as a function of energy, will be something like this. Okay, and the emission spectra correspondingly will be emission intensity as a function of energy. Okay, we'll have some variation like this. Okay, and the two are related through the Shockley-Van Roosbeek relation. We'll use that later on. Also, we'll see that in order to derive this alpha versus E and emission intensity versus E, we'll be dealing with a semiconductor in which it is not a lightly doped semiconductor. Heavy doping effects will come in. Non-K conservation rule will come in. And so there will be many modifications to the existing theory of optical absorption in a semiconductor. And we'll see that it is not a trivial problem to get agreement between experiment and theory. We'll compare experiment and theory, optical absorption, and experiment and theory of the emission process. And we'll see that certain approximations have to be made in order to get agreement with experiment. Okay. Let's start right at the beginning using the Einstein relation which we had derived, and we had shown that for a two-level system, the Einstein coefficients were A and B coefficients were related by 8 pi n bar, that's the refractive index, E21 is the energy, squared over h cubed c cubed B21. And B12, this is the spontaneous emission, this is the stimulated emission, and the absorption is given by B12 is equal to B21. Okay, so we had derived this earlier. Now, if we examine the net stimulated rate, emission rate, obviously, R21, that is the net stimulated, so it is the downward process minus the R21 is the downward process minus R12 is the upward process. And from this we can find that R21 stimulated is equal to 821. The Fermi function, difference between the Fermi functions, okay, higher state and upper state and lower state over the distribution function E21 by KT minus 1. And if this can be written as R stimulated E21, absorbing the exponential factor, we can write this as A21 F2 minus F1. And what is absorption? Absorption, R12 absorption is B12, the upward term, F1 minus F2 into the phonon density, phonon flux at this energy E21. Okay. Sorry, photon flux. This is the photon flux. So for two discrete level system, alpha E21 is equal to R12 absorbed over F E21. This can be written as R12 absorbed over P. This is E21 into the group velocity of the photons Vg, and this can be written as B12 F1 minus F2 this is an important relation over and C by n bar. That's the velocity, group velocity of the wave. So this is the absorption coefficient, which is related to B12, Einstein coefficient, and the difference between the Fermi functions F1 and F2. We can use the actual values of B12, etc., and we then can get E alpha E21 is equal to, just by substitution of the values of B21, h cubed c squared 8 pi n bar squared E21 squared. So absorption is related to stimulated emission E21. So that is an important relation. Now, to calculate, to find B21 from first principles, not in terms of the other coefficients, okay. Sorry, B12, which was in the B12, we use Fermi's golden rule, which you've studied in courses in quantum mechanics. B12 is pi by twice h, and it is the matrix element going from, it's the psi 1 RT complex conjugate, the perturbing potential, perturbing part of the Hamiltonian H1 into the final state. This is the probability of going from making a transition from ground state 1 to excited state 2. So you have psi 2 R2 T and this squared, where H1 RT, we can say this is some H1R, and the T variation we can say is sort of a cosine type of variation. Okay. now what is H prime actually? I'll indicate the steps without going into all the mathematical details. So this is the interaction Hamiltonian, and it is due to the interaction of the electromagnetic wave so with the electron hole system. So it's given by where A is the vector potential and P is the momentum. So this is what we have to use for H1, and if we substitute, then B12 comes to pi q squared H cross m squared epsilon 0 n bar squared H cross omega, and this matrix element becomes psi 1 complex conjugate R P vector momentum psi 2 R squared. Now we can define the momentum matrix element M as psi 1 star R P psi 2 R, and which becomes an integral over the volume psi 1 star R P psi 2 R d cubed R. And you can see the psi 1 star P psi 2, this is what is known as a dipole matrix element. Because dipole is P into distance d, so that is typical. So if we use this and substitute in this expression, then we get the term B12 is pi q squared H cross over m squared epsilon 0 n bar squared H cross omega into this matrix element squared. So in order to calculate the optical absorption, okay, there's another point that we can make, that often we talk about oscillator strengths for a particular transition. Even in classical optics, and the oscillator strength is in this case is just 2 by this matrix element squared over H cross omega m. Okay? This is the oscillator strength. So this is the Einstein coefficient for absorption for transition from 1 to 2 state, and is given by this matrix element squared for a two-level system. Now if we want to go to a solid, a semiconductor which has bands, then obviously we have to look at the density of states, the initial states and the final states. The initial conduction band density of state rho c, E minus EC, where EC is the conduction band level, is given by the well-known expression, okay, this is Mn, okay, H squared to the power 3 by 2, usual NC type of relation, E minus EC to the power half. This is for a lightly doped semiconductor. For the general expression for density of states in the conduction band, similarly for the valence band, it will be EV minus E 2 pi, I think there's a squared here, so minus, so this is the NC type of, this NV type of term, NMP for holes, H squared 3 by 2 EV minus E. So overall, in order to calculate the absorption coefficient, we have to, this is the density of initial states, this is the density of final states. The Fermi function comes in to give the number of electrons actually in this state, number of holes in this state, and we have to use this matrix element for giving the transition probability. Okay, so later on we'll see that this density of states has to be modified because we are talking about now heavily doped materials. For PN, remember the condition for population inversion was that F2 minus F1, okay, was greater than EC minus EV. Okay, this is the population inversion that. So in order to achieve that, we really are dealing with reasonably heavily doped systems. Now, in a semiconductor, what is alpha H cross omega? Alpha H cross omega will be, there will be a band of states, so there's integration over energy, B12 over C by n bar, coming from the original. This expression we had used before, F1 into F1 minus F2. And now the density of the initial states is rho V, this is rho EV minus E, okay, into rho C, E minus EC, okay. And the conservation rule gives you, K conservation rule, energy conservation rule gives you delta E2 minus E1 minus H cross omega, okay, DE. Okay, this is the density of the filled states, this is the density of the empty states, and this is the delta function. So this can be rewritten if you shift, this is just a mathematical shift EV upwards by H cross omega, that's the energy, and this can be rewritten as alpha E is pi q squared H cross epsilon 0 and 0 squared C n bar E rho C E dashed. Okay, so this, it just changing this into rho C E dashed, rho V E double dashed. The matrix element M E dashed, E double dashed, squared, and this function, Fermi function F E double prime minus F E prime dE prime. So this is the relation as derived in typically in Casey and Panish. For alpha, similarly, we could derive relations for R spontaneous, E the rate of, and R the rate of stimulated emission. Okay, these are known. Now, from that relation, to find alpha E and really plot it, I will take recourse to graphical plots to compare experiment with theory. What do we have to know? We have to know rho C E dashed, rho V E double dashed, and this matrix element. And this is not all that straightforward, because now we have to consider effects like heavy doping. That's why right at the beginning I had devoted practically one lecture to looking at heavy doping effects. And so the density of states becomes concentration dependent. There's band tailing. And also we'll see what approximations have to be made for this matrix element. It turns out that this density of states expression becomes, I'll just look at rho c E dashed is twice, say, eta c to the power half mn to the power 3 by 2 pi squared h cubed into E dashed minus EC to the power divided by E eta c, where eta c is root 2 VRMS, where VRMS now is the potential fluctuation, the amplitude of the potential fluctuations due to impurities. For example, with heavy doping, we no longer have a periodic potential like this. Okay. But every now and then, if the impurity concentration Ni is of the order of, say, 10 to the power 18 per centimeter cubed, okay, every now and then we'll have an impurity where the potential fluctuation will be perturbed, and we have to take that into account. Okay, well, sorry. This is a function y E dash minus EC, where y x is x minus z to the power half exponential minus z squared dz. So this exponential minus e to the power minus z squared is a sort of a Gaussian distribution. Okay, and what is this VRMS in physical terms? VRMS is q squared over 4 pi epsilon. That's the dielectric constant, 2 pi, and the fluctuations are due to the donors and acceptors present, Na plus Na minus Ls where Ls is an important parameter. It's the screening length. If you have any charge, then what is the length beyond which this effect of the charge is screened? So Ls is also known. 1 by Ls squared is q squared epsilon kt rho e. So in principle, Nd and Nd plus Nd minus, remember that even if the material is N-type, there may be some acceptors. Even if it's P-type, there may be some donors. So compensation is also coming in. And so now we have in this expression, we know what eta c is in terms of VRMS. VRMS we've just written out. So in principle, this sort of density of states can be calculated. Okay. Let's go to now sort of a graphical representation of this density of states and this Gaussian density of states is also called the Kane band tail model. In which if you plot, okay, we are plotting energy this way and density of states this way. For the case of, for normal lightly doped semiconductors, what do we assume? We assume that there is a sort of a parabolic band. Okay, so for parabolic band, the density of states will be something like this. This is the conduction band, and most of these calculations are done with parameters for gallium arsenide. So for density of states in the conduction band depends upon the electron effective mass, so that's rather low, 5^19, whereas for the valence band density of states, parabolic band goes something like that. Okay, and this is something like 10^21. So this is rho, we are looking at rho C and looking at rho V. Okay. Now it turns out, and of course these values are in per centimeter cube per electron volts. Okay. Now physically, the material that we are dealing with in lasers is not okay. Let's say the energies, that is 0, and this is minus 1.4. This is in electron volts. Is not lightly doped. It is much more strongly doped. Then the density of states is no longer like this. There is this band tailing effect. Okay, what does band tailing mean? That band tailing means that the effect of the perturbation is to shift the conduction band down like that and the valence band up. Okay, and the shifting depends upon the concentration of, it's concentration dependent. So this one, say, is for 1/1018 per centimeter cube. Okay, now if the doping concentration goes up, then we have a series of, this is a little exaggerated, but this next one will be for, say, 3×1018, then 10^19. We maintain that this is Gaussian, and this is the old parabolic band. So we have to calculate the optical absorption using this concentration dependent band tailing, which is Gaussian. Well, why is that necessary? Because otherwise we do not get agreement with experiment. Okay. I'll compare this with experiment later on, but it turns out that this model also is not good enough, and the next model that was taken is called the halperin-lax model, HL for short. And the halperin-lax model has the addition that the kinetic energy of carriers are taken into account. So what is this halperin-lax? The halperin-lax model is depicted as follows. Density of states here and the energies this side. What is done is it is a parabolic band at high energies, parabolic band here at high energies, and it is the halperin-lax band tailing here, okay, and there is interpolation to match. So this is the valence band and this is the conduction band, okay, and obviously these are the band gaps. So this is the halperin-lax band tail model, which is taking into account the kinetic energy of the carriers. Okay. Let me just explain why this is necessary, and later on I will talk about the matrix elements. I've just talked about the density of states, because even if you want to look at the optical absorption alpha, which is very easily measured, okay, optical absorption in gallium arsenide, okay, you're not talking about ternaries or quaternaries. This is alpha against E. If we use the parabolic model, if you want to calculate alpha, you're just using a parabolic model without any band tailing, we get a variation of alpha just like that, okay, very sharp, and the energy obviously is here something like 1 point. This is 1.40. This is 1.55, 1.35, etc. Let's compare this with experiment. With experiment, we find that the experimental results are quite different. They are something like this is experiment. P0 is reasonably heavily 10 to the power 1.2 10 to the power 18. Okay. So temperature is important. T is 297 K. Okay. So you see there's wide divergence between, not only is the shape different, the cutoff energy is different, the saturation is different, the whole nature of this optical absorption is different. Now, so that's why the different band tailing effects have been taken into account. And if we have, if we take the constant matrix element, we are taking that M as constant, and if you do calculations with the Kane model, then we find that the so this is Kane model, and if we have a constant matrix element, okay, then it diverges somewhat. Okay, so immediately you see that this Kane model of band tailing does give you better agreement. However, the agreement is not as good as is obtained with the halperin-lax model. Okay, so you see simple theory, parabolic, okay, experiment, Kane model, exponential. It is giving better agreement here, but still the nature, the shape of this curve is different. Now, using the Van Rosbeck-Shockley relation, we can go from this alpha versus E curve, we can go quite easily to theoretical determination of the relative intensity. Okay, that is absorption. Now we go to emission. again gallium arsenide 297, and this is okay. For parabolic bands, what do we get? Parabolic bands, extremely sharp. Let's see. Okay. If we calculate from experiment, then what do we get? We get something like this. It's not only broader, it is shifted. This is calculated from alpha, experimental graph. Okay, and if we use the Kane model, then what do we get? We get something. We get a bit of a tail. We get a bit of a tail. Okay, so this is the Kane model. So you see that even calculation of a simple thing such as the optical absorption, from which we get the emission data, does require including of the heavy doping effects, potential fluctuations, and we get a slightly better agreement with experiment if we use this, okay, as opposed to the simple parabolic model. And this is, we call it the constant matrix element, constant M. Okay, so I'll stop here today. Next time I will discuss what is called the halperin lax model, and then there is a improved model called Gaussian halperin lax band tail model. Okay. These give better agreement, and I'll also talk about the matrix element M. The first approximation, we take constant matrix element, constant meaning it's independent of energy. Then we take a case where it is energy dependent, which gives you better agreement. And finally there is Stern's modified matrix element. So I'll go on to this next time, and I'll show that even for calculation of emission spectra, absorption spectra of a simple semiconductor like gallium arsenide, all these corrections have to be made in order to get a good agreement.